Okay, today's notes is on the central limit theorem. I'm going to start off by talking about it, by writing it down, what it says. The central limit theorem says this. No matter what we are measuring, the distribution of any measure across all possible samples we can take approximates a normal distribution. Normal distribution. As long as we have enough samples. N greater than or equal to 30. We mentioned this earlier. The actual title of it is the central limit theorem. No matter what we're measuring, it doesn't matter if you're looking at the median, it doesn't matter if you're looking at the mode, the mean, no matter what piece of data, if you look at any data, if you take the distribution of that measurement across all possible samples, provided that you have at least 30 or more, the distribution of that piece of information across all those samples will be approximately a normal distribution model. Okay, we've talked about this already. We talked about if you look at income, it's always going to be skewed. It's always going to be skewed. But if we take the mode of this income, and then we compare another set of incomes, and we look at the mode of that income, and we repeat that n more than or equal to 30 times. If we were to take a bunch of samples, as long as you do it at least 30 times, and you're to compare all of the modes, so we'll call it mode 1, mode 2, so on and so forth, up to mode n, where n is more than or equal to 30, and you were to put all of those modes into its own distribution model, that model will be normal. Okay, we've already said this, but that's what the central limit theorem says. Guys, there's a few questions on the test about the central limit theorem that just simply say, is this true or false? So we're going to label this things to know. What we're getting ready to write down, I'm telling you, there's questions on the test. It's just going to be questions based around, do you know this, what we're getting ready to write. Things to know. First one. The mean of all samples. The mean of all sample means, if you were to take all of the samples, all your different samples, and look at the average of those samples, and then you were to take all of those averages and then average them together, the average or the mean of all the sample means should equal to what? The population mean. The mean of all samples, it equals the population mean. If you're to take the mean of all the samples, that should equal the same as the population mean. That's something the central limit theorem guarantees. Okay? Something else. The standard deviation of all sample means. Is the population standard deviation the population standard deviation divided by, which you sign in here, the square root. Oh, you just got here? Okay. Of the sample size. The standard deviation of all the sample means is equal to the population standard deviation divided by the square root of the sample size. If you remember when we did the standard deviation over proportion, it was the square root of p times q divided by what? N. The square root of a fraction is equal to the square root of the top times the square root of the bottom. That would make the bottom of that fraction the square root of n. So we're dividing the population standard deviation by the square root of the sample size, square root of n. Yeah, that's all I'd say. Okay, as
can you draw what that equation could be?
it changes from problem to problem.
Oh.
Because if you're dealing with proportion, it's the square root of p times q divided by n. But if it's not a proportion, if it's like if you're looking at means, or if you're looking at modes, or any other quantitative data, it has a different formula.
Will you write them at some point?
We will, yeah. There will be 3 different formulas, and we'll get to that.
Q minus P, or P times Q over N.
As sample size increases. As sample size increases, as the sample size increases, does the sample mean change? Theoretically, the sample mean shouldn't change. If it's 40% is Democrat, if you ask 100 people, it should be 40%. If you ask 1,000 people, it should still be 40%, right? The sample size, the sample mean does not change, but the standard deviation does what?
Goes down.
It decreases. Okay, so as sample size increases, sample mean remains constant, remains the same. Sample standard deviation decreases. As you ask more and more of your population, you're getting a more and more accurate answer. Therefore, your confidence interval is going to get smaller. Okay? Because you're covering more of the population, you're going to make a more accurate prediction. So sample standard deviation decreases. Okay? The distribution of sample means. The distribution of sample means. So what we're talking about is how all of your means of all your different samples are distributed. If you take a bunch of different samples, you'll get the mean of each. The central limit theorem says that distribution of those sample means should be what kind of distribution? So it approaches normality. The distribution of sample means approach normality. The distribution of sample data so we're talking about the data of each individual sample. The distribution of that sample's data. Will it approach normality? No. If you go ask a bunch of people about their income, just because you've done that 30 times, if you go out and do it a 31st time, you're not guaranteed that that 31st collection is going to be normal. It's the collection of the means that's normal. So the distribution of sample data does not approach normality. Okay? Only the distribution of the sample mean, not the distribution of the data itself. The distribution of sample data does not approach normality. Okay, there's going to be a couple questions in the test. That's going to be which of the following is true, and it's going to involve answers that involve this.
I just noticed that your lowercase n is like
Yeah, well, mom, anytime she writes like an important note, she uses all capital letters. And a lot of like, I would say 1950s, 1960s, that term, that was a popular concept that was taught in the schools, was especially in science class. Science classes use all capital letters.
Your mom and my mom are the same age, but you're like 20 years older than me.
I'm not 20 years older than you.
You are. You're like
I'm like-
40. You're like 80.
I'm like
You're older than
9
your
to 10 years older than you.
You're like
50 years older.
You're 50 years older than your own mother. It's the same age as my mom. How are you existing?
Yeah, you reported all that.
I'm not biased at all. Everything I say is completely true.
Except for the fact that I'm 20 years older than you.
No, that's true. You're also 80 years old than me at the same time.
That's true. Alright, quantitative data. When you go out and collect, what we're talking about is quantitative measurements. So if you go out and ask everyone's income, it's going to be skewed data, but you repeat that at least 30 times, and then take the average of all of those samples and compare them. It's going to be normal distribution. If you're to take that and you're to collect it at least 30 times, it should be approximately normal, and the average of all of your samples should approximately be the same as the population mean. Does that make sense to everybody? So, if you remember, we had z-scores. Z-scores dealt with normal distribution. The formula for z, we've had two formulas so far. We've had the data that we're interested in minus the standard deviation, or minus the average of our data, divided by the standard deviation of our data, right? And that's when he was dealing with just one quantitative variable that was already normally distributed. Okay? This is what you're interested in minus what should happen, the mean. If I said the class scored an average of a 70 on a test, and you were to pick someone randomly, theoretically they should have a 70 because that's the average, divided by the standard deviation of our data. We then had z-scores equal p hat minus p over the standard deviation of p hat. What our sample says minus what the population proportion says it should be, divided by the standard deviation of p hat. But now if we're dealing with quantitative data, we're not talking about proportions. We're going to have an actual specific numerical value. We're doing a mean of means, or the average of the modes. There's going to be a numerical value. And the average of all those sample means should be the what? The average of all the sample means is the population mean. All right, so what we have now with this is we have what's called the population mean. If you were to go ask, people in Adams County, how much money do you make? It's going to be, and you were to ask, say, 60 people. It's going to be a skewed data set. You do that 30 times, you're going to have 30 skewed data sets. But then if you were to look at the average of each of those data sets, and then look at the normal distribution of those averages, what's in the middle of that model should be an exact approximation or the exact representation for the average of the entire county. Right? That's what this central limit theorem says. So we have a population mean. The notation for this is now called mu.
Oh, why do you?
Mu. It's a Greek letter. It looks like an M and a U. Had a baby. Right? Mu. It's a Greek M. The Greek M. It looks like the M. Okay, so population mean is called mu.
Oh, that's the thing from chemistry. Like that.
We also have our sample mean. Our sample mean. What's our notation for sample mean been all year?
Why had?
Mm-mm.
Nobody had. Somebody had. Don't judge me.
X bar. The average of our sample is denoted with X bar. So we have sample mean, population mean. We've also got population standard deviation. The standard deviation of the entire population. It uses the lowercase sigma. There's lowercase Greek letters. Yep. The lowercase sigma. It's like a 6 that's been turned on its side, or a 9 that's been turned on its side, depending on if you're how you visually see those. I see a 6 on a 9.
I just see a
I
circle.
just see a circle with a line on it.
Yeah. So,
It's a circle.
and then we have our sample standard deviation, which is, we're going to write this as S sub x. And what did we write on the previous page? The sample standard deviation is the population standard deviation divided by, so it's the population standard deviation, which is known as sigma, divided by the square root of our sample size, which is n. That's the formula for our sample standard deviation. Now, let's think about this. If we go out and we collect data, what should happen? The mean of our data should be the same as what? If I said if I said the average income of an Adams County household is $36,000, and you got 100 households, their average income, you should get 36,000. So if you collect a sample, theoretically, you should get the population mean. But will that always happen? No, there's error in your study, right? You may be off a little bit. The way we measure how much error is, we use a z-score. It's the same concept. The z-scores tell you how far your sample is from the predicted, which is the population mean. And how far we are from the population mean is dependent upon our standard deviation. So what we have now with quantitative data, we still have a normal distribution model. Directly in the middle of our curve, if we go collect data, what should happen? We should get the population mean. So mu is in the middle. What was in the middle of proportions?
Mean
What was in the middle of proportions? P or P hat?
P.
P, because that's your population proportion. That's what should happen. It's the exact same concept. It's with numerical, quantitative data, not proportions. Okay, so we've got mu, and then we have a formula for standard deviation.
Hey, is the difference between micro, is that the same thing as micro?
I'm not sure what you're
Because
talking
in
about.
physics, that symbol means micro. But I don't know, is it the loop? Is there a loop in it? Or is that how you just do it?
It's a Greek letter mu. It's just used to denote a microgram.
Oh, okay.
But the actual symbol is called a mu. But
Alright.
that symbol is used to denote micro.
Okay, so but that's the same symbol?
That's the same symbol.
Okay.
Same symbol. Okay, so, and then how far we are from the average is dependent upon the standard deviation. The standard deviation is dependent upon your sample size. How many people you asked. Okay? So we can come with the confidence. So let's go through here. We've got a z-score formula. We have a z-score formula. It's always what we get, which in terms of means, what we get is that the population or the sample mean?
Sample.
The sample mean. So it's x bar minus what we should get, and if we've done everything correct and it works out perfect, we should get the mu, so it's x bar minus mu,
I just like drawing.
divided by the standard deviation of our data, which is the sample standard deviation. So it's divided by the population over the square root of n.
You know, back to get serious whenever you're drawing imaginary words. It's great.
Does everyone see how this ties into the same concept we've been doing the last 4 weeks?
Yeah.
It's the exact same formula, but it's the variable that we're dealing with. When we're dealing with one set of data where we're just doing a data analysis, we want to know what's the probability that this kid does, how does he do in comparison to his class. Well, let's think about this. That one kid, if you average one person, it's just equal to that one person. Does that make sense to everybody? So if you look at one kid, the average of your data is just that kid. Now, if you're comparing that kid to his entire class, how he did in comparison to the entire class, then the entire class is your sample, right? So now your population is X bar. And then the standard deviation formula is you take the population standard deviation of the class, divided by the square root of that one kid. What's the square root of 1? 1. So this is the exact same formula that we were doing when we were talking about basic data analysis, where we were just comparing a person to their classmates. Okay? It's just now allowing us to do it in a setting where we're looking at multiple people or multiple items. Okay, depending upon our sample size. And then we also have a 95% confidence interval.
It scares me.
Your 95% confidence interval is 95% of the time we should get a sample mean. Okay? So I'll skip a couple lines. 95% of the time we should get a sample mean. And guys, when we were doing the 95% confidence interval for proportions, it was 95% of the time we should get a sample proportion. It's the exact same concept. Ninety-five percent of the time we should get a sample mean. That is within 2 standard deviations, which is this formula. Population divided by the square root of our sample size. And it was, remember, it was the 2 standard deviations of our p hat of the population proportion, which is p. But in this case, it's not population proportion, it's of the population mean. And that talks about, that's the symbol mu. All we're doing is the exact same concept, but instead of talking about percent Democrat, percent not Democrat, percent smokers, percent not smokers, percentage of accuracy on predicting if someone's gay based on their picture versus not, we're talking about quantitative data. So now this allows us to take, well, if you were to collect data and it's skewed, you'd say, well, crap, we can't do any normal distribution. We cannot use the concept of z-scores. We can't use the concept of p-values. We can't do any of that because it's skewed data. Those only apply to normal data. Central limit theorem says if you were to collect 30 samples, you can then use that distribution of their sample means as a way to talk about that what was skewed data now as normal data. And once you do that, you now open up the doors to bring in z-scores and p-values. So our 95% confidence interval is within 2 standard deviations of mu. So the formula is mu minus 2 standard deviations, comma, mu plus 2 standard deviations. It's the same formula we've always been doing. P minus 2 standard deviations of p hat. P plus 2 standard deviations of p hat. At the beginning of the year, it was x bar minus 2 standard deviations of x, comma, x bar plus 2 standard deviations of x. It's the same exact formula. It's just the context in which we're using that formula.
And you just looks like him. Scary.
All right. Let's get to doing some problems with this.
Oh, God.
Okay. We're going to do a series of, 6 to 8 problems. We're not going to finish it. There will not be homework for the weekend. We will start it today and finish it on Monday. Here's the example we're going to start with. The CDC, the Center for Disease Control, reports 18-year-old women have a mean weight of 143.74 pounds. So the CDC is a company that's large enough that if they report something that's been government approved, then that means we accept it as being the population. The one question we did earlier was the CDC reports that, what was it we did? It was a percentage.
But I got it.
22% of women have a BMI of more than 22 or 25.
Yeah.
Right? So they reported, and that was that 22% of women, that 22% was our population proportion because they said so. So now the CDC is reporting some other fact, but now instead of being a population proportion, this is accepted as being the population mean. So this 143.74 is going to be used as what symbol?
Mu.
Okay? So, with a standard deviation of 51.54 pounds. Now, if they're reporting that, then that means that that is our population standard deviation. Does that make sense to everybody? Which means that that is sigma. That's sigma. Because they're saying this is what we got from our studies. And then it says, a college PE program, physical education program, not talking about PE class. Okay? The college physical education program collected 200 freshman girls' weights and got a mean of 140. Is this abnormally low? It's lower than what the CDC says should happen. It's lower than what the CDC says should happen. The CDC says no matter what sample you take, you should get an average of 143.74 because that's the population mean. So if you were to collect a sample mean, you should get 143.74. We're talking about they collected 200 people, 200 freshman girls' weights, and they got a mean of 140.
That's oddly accurate.
So, well, it's low. Well, it may be. If the standard deviation is really tiny, this actually might be extremely inaccurate.
It says right there 51.54.
But, yeah, well, that's the, but hold on a second. The standard deviation, though, is 51.54 pounds. Okay, so they can say, well, that's pretty accurate. That's 51.54 pounds for how many people, though?
The entire population.
That's just one person.
Ah.
We're talking about doing an average of 200 women. So the standard deviation of our data is not 51.54. It's 51.54 divided by the square root of 200, which makes that standard deviation get a lot smaller because of the sample size. Because of the sample size. So maybe the first thing to do would be to go through and identify all the known information.
Yes.
Okay. So the CDC reports 18-year-old women have a mean weight. They're reporting this. They're a government-funded agency. That's going to be accepted as being our population. So this is our population mean. Okay? That, yeah, well, I tried to. Something on marker doesn't cooperate. Okay, so mu is equal to 143.74. With a standard deviation of 51.54, that's our sigma. That's our population standard deviation. Thank you, ma'am.
No, I need to ask you some questions. Computer.
What is it?
I just need your computer. I need your computer information.
All right, that's our population standard deviation. A college PE program collected 200 freshman girls. So they're looking at a sample size of 200. And they got a mean, so they got a sample mean, which is X bar of 140.
I think we scared her away with statistics.
Statistics. So, if we were to draw a normal distribution curve, directly in the middle should be mu. Directly in the middle should be mu, which is 143.74. Where does 140 fall? Below or above?
Below.
Below. We don't know where at below. We just know below. So I'm going to just put it right here. 140 somewhere on this side. We don't know where. It could be, that line could be completely inaccurately drawn. It could be a lot further to the left. It could be really close to 143. There's two methods to test if it's abnormally low. We can use the z-score method or we can create a 95% confidence interval. if you guys remember, which was the quicker method?
Z-score.
The z-score method. I want to do both methods. We're going to do z-score first. Okay, so z-score method.
So I have a question. On the test, are you gonna you let us choose what method you want to do, or you want to choose a certain
Well, it might. Well, instead of giving it the z-score, it might say what percent. What's the probability that this happened? So then, in order to do the probability, you've got to have the z-score. Okay, because probability is a p-value. P-value means z-score.
Like if you get the sample standard deviation, was that just
Well, I mean, here's what we got. We got what we got, which is the sample mean, minus what they should have got, which is mu, divided by the sample standard deviation, which is S of x. So if we look at the information that we have written up here, do we have x bar? Yes, they got 140. Do we have mu? What should have happened? Yes, 143.74. Do we have our sample standard deviation? No, but we have a formula for it.
I'm sorry, I really have.
Go ahead.
If you just get the sample standard deviation, could you just subtract that from the population mean,
Twice.
and that would you just said okay.
Because it's 95% of the time you should be within 2 standard deviations. So yes, you could. And that's doing the 95% common interval method. We're subtracting it twice.
So like you would actually need to get a z-score. You just really need to get the sample standard deviation for this specific time.
If you want to do it with the 95% common interval method, yes.
Oh,
We're going to do it both methods.
Can you just, if you're figuring out that formula, can you just put that under that?
Yeah, you can go ahead and write it.
Under it?
Yeah, but when you first read the problem, that's not initially told you.
Okay.
So that, that's not something that you go, okay, I know this. I mean, that's something you've got to think about.
All right.
And trying to figure out the z-score formula is what says, hey, I need to know this. So we take the sample, or we take the population, which is 51.54, we divide by the square root of 200.
It is 3.64444.
3.644444.
Wasn't it? Then I was at
Okay. We'll use 3.64. So now look, the standard deviation was 51. Okay? Which made it look like, well, 140 is really close because the standard deviation is 51. But when you're talking about a sample size of 200 people, the standard deviation of the average of those people being 143 is only 3.64. That's not that far away now. Okay, so that's pretty close. It's within one standard. It's almost within one standard deviation. Because how far is 140 and 143.74 separated? 3.74. We've got 3.64. So it's just a little bit below -1. Okay? So now we figure out the z-score formula. We plug all this information in. What they got, taking away what they should have gotten based on the national report, divided by the standard deviation, which is based on the sample size of 200. You get -1 point something.
0.26.
Okay, so -1.026,
Yeah.
that'd be -1.03. Because remember when we do if it asked us what's the probability of this occurring, if they said if this question was to instead say, is this abnormally low, and they said, what's the probability of this occurring, then we would just find a p-value that corresponds to -1.03.
if you did it with the 95% confidence interval, you wouldn't need to get a p-value.
Correct. But it just once again, though, it's all the same concept, it's just depending on what they're asking. So they ask what's the probability of getting an average of less than 140, then you would use the p-value to get the answer to that kind of question. Shannon, you have a question?
I didn't get that.
You make sure you subtract the top, hit enter, and then divide by 3.64.
That's what I did. I got -0.953.
Oh, she got their numbers wrong. It's 74, not 47.
Oh.
Okay, so we get -1.03. Remember, the z-score method says you ask yourself, does the absolute value of z is the absolute value less than 2? Is the absolute value of -1.03 less than 2?
Yeah.
Yes,
Oh, yeah.
because 1.03 is less than 2. So that means it is inside of the 95% confidence interval. Okay, so if this is true, a sample of 200 with a mean of 140 is within 2 standard deviations of mu. Thus, is this abnormally low?
No.
No. This is not abnormally low. It's in the range, it's in the 95% confidence interval. That means 95% of the time this should happen. It's in that value, it's in that window of rate values. That means that this is not abnormal to happen. That's the Z-score method. We're going to do the same question using the 95% confidence interval.
Can we like tune out now if we want to do that part?
Yeah, do you want us to write that?
It depends on the context of the question that's being asked.
So,
Okay. Some of the questions might ask, just report the 95% confidence interval. So you don't even know how to get it. The 95% confidence interval is mu minus 2 standard deviations, comma mu plus 2 standard deviations. And actually, this is a pretty easy, pretty quick result because we've already got mu and we've already done S of x, right?
Yeah.
So I mean, this is just a matter of substitution. Mu is 143.74 minus 2 3.64s. 143.74 plus 2 3.64s. You get a range of values of 136.46, and changing that to an addition, you get 151.02. Now, a question might be, report the result of a 95% confidence interval for a sample size of 200. So we would say 95% of the time, or we could say we are 95% confident that a sample size of 200 will result in a sample mean between 136.5 and 151 pounds. Does that make sense? So 95% of the time, a sample of 200 will result in a mean, a sample mean, between 136.5 and 151 pounds. What did this college get?
140.
140. So since, is 140 an element of this interval?
Yes.
Yes. So since 140 is an element of this interval, this is not abnormally low. We get the exact same result. It falls in the interval of what should happen 95% of the time. Therefore, it is not abnormally low for a study of 200 people to result in an average mean of 100 or an average sample